Vectors. All motions we've been considering are rectilinear, that is, along a straight line. Now we must go one step further. We begin understanding the laws of nature by analyzing the simplest cases and leaving out of our first attempts all intricate complications. A straight line is simpler than a curve. It is, however, impossible to be satisfied with the understanding of rectilinear motion alone. The motions of the moon, the earth, and the planets, just those which are the principles of mechanics, have been applied with such brilliant success, are motions along curved paths. Passing from rectilinear motion to motion along the curved path bring new difficulties. We must have the courage to overcome them if we wish to understand the principles of classical mechanics, which first gave us first clues, and so form the starting point for the development of science. Let us consider another idealized experiment in which the perfect sphere rolls uniformly on a smooth table. We know that if the sphere is given a push, that is, if an external force is applied, the velocity will be changed. Now suppose that the direction of the blow is not, as in the example of the cart, in the first line of motion, but in quite a different direction, say perpendicular to that line. What happens to the sphere? Three stages of motion can be distinguished: the initial motion, the action of the force, and the final motion after the force has ceased to act. According to the law of inertia, the velocities before and after the action of the force are both perfectly uniform. But there is a difference between the uniform motion before and after the action of the force. The direction is changed. The initial path of the sphere and the direction of the force are perpendicular to each other. The final motion will be along neither of these two lines, but somewhere between them. Near the direction of the force, if the blow is a hard one, and the initial velocity, small. Near the original line of motion, if the blow is gentle and the initial velocity great. Our new conclusion, based on the law of inertia, is, in general, the action of an external force changes not only the speed but also the direction of the motion. An understanding of this fact prepares us for the generalization introduced to physics by the concept of vectors. We can continue to use our straightforward method of reasoning. The starting point is again Galileo's law of inertia. We are still far from exhausting the consequences of this valuable clue to the puzzle of motion. Let us consider two spheres moving in different directions on a smooth table. So as to have a definite picture, we may assume the two directions perpendicular to each other. Since there are no external forces acting, the motions are perfectly uniform. Suppose further that the speeds are equal, that is, both cover the same distance in the same interval of the time. But it's correct to say that the two spheres have the same velocity? The answer can be yes or no. If the speedometers of both cars show 40 miles per hour, it is usual to say that they have the same speed or velocity, no matter in which direction they are traveling. But science must create its own language, its own concept for its own use. Scientific constants often begin with those used in ordinary language for the affairs of everyday life, but they develop quite differently. They are transformed and lose ambiguity associated with them in ordinary language, gaining vigorousness so that they may be applied to scientific thought. From the physicist's point of view, it is advantageous to say that the velocity of the two spheres moving in different directions are different, although purely a matter of convention. It is more convenient to say that four cars traveling away from the same traffic circle on different roads do not have the same velocity, even though their speeds are registered on the speedometers are all 40 miles an hour. This differentiation between speed and velocity illustrates how physics, starting with a concept used in everyday life, changes in a way which proves fruitful in the further development of science. If a length is measured, the result is expressed as a number of units. The length of a stick may be 3 feet, 7 inches, the weight of some object 2 pounds 3 ounces. A measured time may be so many minutes or seconds. In each of these cases, the result is measurement is expressed by a number. A number alone is, however, insufficient for describing some physical concept. The recognition of this fact marks a distinct advance in scientific investigation. A direction as well as a number is essential for the characterization of a velocity. For example, such a quantity possessing both magnitude and direction is called a vector. A suitable symbol for it is an arrow. Velocity may be represented by an arrow, or briefly speaking, by a vector whose length in some chosen scale of units is measured of the speed and whose direction is that of the motion. If four cars diverge with an equal speed from a traffic circle, their velocities can be represented by four vectors in the same length as seen from our last image of going in four different directions. In the scale, use 1 inch stands for 40 miles an hour. In this way, any velocity can be denoted by a vector. and conversely, if a scale is known, one may ascertain the velocity from such a vector diagram. If two cars pass each other on the highway and their speedometers both show 40 miles an hour, we characterize their velocities by two different vectors with arrows pointing the opposite directions. So the arrows indicating up-down or downtown subway trains must be pointing in opposite directions. But all trains moving up-down at different stations or on different avenues with the same speed have the same velocity, which may be represented by a single vector. There is nothing about a vector to indicate which stations the train passes or on which of its many parallel tracks is it running. In other words, according to the accepted convention, all such vectors as drawn below may be regarded as equal. They're all of the same length, they're all of equal speed. They lie along the same or parallel lines, are of equal length, and finally have arrows pointing in the same direction. And if arrows are going in all different directions because they have either different length or direction or different or both, they are same four vectors and may be drawn in another way, which they all diverge from. So if you have three arrows going out from a common point, since the starting point does not matter, these vectors can represent the velocities of four cars moving away from the same traffic circle, or the velocities of four cars in different parts of the country traveling with the indicated speeds in the indicated directions. The vector representation may now be used to describe the facts previously discussed concerning rectilinear motion. We talked of a cart moving uniformly in a straight line and receiving a push in the direction of its motion, which increases its velocity. Graphically, this may be represented by two vectors, a short one, denoting the velocity before the push, and a longer one, denoting the velocity after the push. The meaning of the dotted vector is clear, and it represents the change in velocity for which as we know, the push is responsible. For the case that the force is directed against the motion, there is a motion that is slowed down. The diagram is different. The first line is longer and the second line is shorter. Along the dotted vector corresponds to a change in velocity, but in this case the direction is different. It is clear that not only velocities themselves, but also their changes are vectors. But every change in velocity is due to the action of the external force. Thus the force must also be represented by a vector. In order to characterize a force, it is not sufficient to state how hard we push the cart. We must also say in the direction we push. The force, like the velocity, or its change, must be represented by a vector and not by a number alone. Therefore, the external force is also a vector and must have the same direction as the change in velocity. In the last two drawings, the dotted vectors show the direction of the force as truly as they indicate the change in velocity. Here, the skeptic may remark that he sees no advantage in the introduction of vectors. All that has been accomplished is the translation of previously recognized facts into an unfamiliar and complicated language. At this stage, it would indeed be difficult to convince him that he is wrong. For the moment, he is in fact right. But we shall see that just strange language leads to an important generalization in which vectors appear to be essential.